program committee selected the next paper. It was written by Matt Wentzel-Long. We accepted it, and then Matt was not able to even participate by Zoom. Luckily, his co-author, Jeff Landis, was already accepted for a completely different paper. Jeff, if you can confirm you're online, I'll give you the mic.
Well, thanks. Yeah, I would like to start by acknowledging my co-author, Matt Wentzel-Long, who did the computational work I'll be presenting, which is sort of by far the lion's share of some of this work. So thanks a lot, Matt. Good work. We're talking about the question of power for an interstellar probe. So as we know, several people are looking at the idea of ultra lightweight interstellar missions that could reach Alpha Centauri in as little as a 20-year interstellar cruise at 20% of the speed of light. But next slide, please. The difficulty here is that these are extremely lightweight missions. They're essentially chipsets. So how do you do anything once you get there if your payload mass is measured in grams? And there's many aspects to the question, how do you do anything? We just heard a paper talking about how do you communicate. Well, one of the problems is power. How do you communicate needs power. How do you make sensors? What do you do once you get there without power? So the power source for this interstellar microprobe is just an extremely difficult power system. Nobody has something that can produce the amount of power needed within the mass limits. Next slide, please. The baseline system we looked at was something very much like Starshot, and thanks to the Cornell people for showing off this little chipset. That would be the type of payload that we'd have. The payload would be about 3 grams. And in fact, you accelerate it up to 20% of the speed of light at 15,000 Gs. So you need a relatively robust system. Then you have 20 years to wait before anything happens. And then you spend roughly 5,000 seconds flying by the planet. Next slide, please. So this is what we're looking at. Well, we need power for a lot of different things. The driver that we decided to look at was the power for data return. We were assuming some sort of laser communications. We were assuming probably we could continue to downlink for a year after the encounter, but we might need higher power for a brief time. And we basically assumed that the power requirement was in fact an energy requirement. So for this study, we made a straw man energy requirement of 300 kilojoules. Next slide. There's a lot of different approaches to power. In fact, back in 2019 at the Wichita workshop, I gave sort of a summary of these approaches. Weight is the critical parameter. So this particular work is looking at generating power from moving through the plasma and magnetic environment of the target star. Next slide, yeah. So specifically, we're looking at, can we generate power from the motion of the spacecraft through the ambient plasma and magnetic fields? And we looked at this both in the interplanetary environment, as we did the encounter, and also in the interstellar environment when we're just cruising through free space. So the question is, can we get something on the order of 300 kilojoules? Next slide, please. So the voltage induced in the passage through the magnetic field is simply the V cross B potential. We actually also looked at the idea of perhaps we could get power out of the kinetic energy of the incident protons and electrons. That turned out to be pretty difficult. So we, after a while, homed in on the idea we can use the magnetic field of the target star. So next, click once. There's a B field. We have a velocity. V cross B gives you, next slide, a E field. That induced E field, click one more time, please. The E cross B B field gives you a basically an electric field similar to an electrodynamic tether. Next slide. The current, however, needs to be closed. We can't generate energy just from an electric field. We need to pass current. All current flows in a loop. You can't have one-way current flow. So the way we close the current loop is to capture electrons from the interplanetary medium. At the speed we're traveling, the protons will move right through a thin sail, but the electrons can be captured. So those electrons are captured. Then by some sort of cold cathode emission, we can eject those electrons at one end of the sail. You might ask, well, what happens if the medium is not ionized? Well, it turns out that's not really a problem. At 0.2 speed of light, the neutral hydrogen will be stripped to be electrons. So it will be ionized, whether you want it to be ionized or not. So next slide. So here's a view of what the magnetic field of stars actually looks like. I always sort of pictured magnetic fields as dipoles, but in fact, as Parker told us back in the 1950s, in fact, the magnetic fields spiral around the stars. Next slide. So it spirals around because the solar wind is ejecting particles. These particles spiral around the electric field. As the sun rotates, the motion of the moving particles sort of winds these magnetic fields around the star in this Parker spiral pattern. Next slide. So we scale this in spherical coordinates. Conveniently, we scale it from the B field at the Earth, and then we calibrate it with Voyager 1 and 2 data that gives you the radial portion. So you then have the solar wind moving outward at a typical velocity of about 400 kilometers per second. You can fit that to give you the number of electrons per cubic centimeter. Next slide. Turns out the power is now proportional to the current times the voltage. The voltage is proportional to the V cross B potential, but the current is going to be proportional to the area. So the result is that the power is proportional to the length, the characteristic length cubed, or if you prefer, think of it as area to the 3/2 power. So we're normalizing all this power into units of power per unit area per unit length. Comes out in those odd units of watts per cubic meter. Next slide. So here's a typical graph. This is now coming into a planetary system of a sun-like star. The word sun-like star means we're assuming that the magnetic field and the plasma density is exactly equal to the sun's magnetic field and energy density. You're coming in from the right. On the rightmost slide, you see us moving from 120 AU into 20 AU. Then on the leftmost plot is the little bit further in from 20 AU down to about 2 AU. You can see that the power rises extremely quickly as you get close to the star, where both the magnetic field and also the density of the plasma rises, but it's still measured in fractions of a microwatt per cubic meter. Next slide. Next slide looks into Proxima Centauri. Turns out Proxima Centauri looks a lot better. It's a pretty dim little red dwarf star, but turns out red dwarf stars have powerful magnetic fields. Who would have thought? And they put out a moderate amount of solar wind. So now we're looking at something where as you come in from infinity, the power raises to levels actually of milliwatts per cubic meter, not merely microwatts per cubic meter. But now let's look at that actual flyby of a putative planet. Next slide, please. Here is a graph where we show a flyby at a distance from the star of about 1 astronomical unit. And this now depends a little bit on what angle you come in, both the angle from the planetary ecliptic as well as the angle from the magnetic equator. I'll look at that in a second. But this is the Sun-like star. You can see for that critical distance when you're passing the star, actually power drops to near zero just for a second as you reach the point where you're moving parallel to the magnetic field, but you're getting power that comes up to a peak value now of about, maybe 12 microwatts per cubic meter. Just for reference, a Starshot solar sail, circular with a diameter somewhere on the order of 4 meters, would have a R cubed for the sail coming about 50 cubic meters. So multiply that by 50 to get power for a Starshot size sail. It's still pretty small. It's still barely coming up into the milliwatt level. Next slide, please. Looks a lot better, oddly enough, if we're looking for a 0.5 AU flyby of a planet of Proxima Centauri. Now we're getting power in that critical distance, about 0.5 AU to negative 0.5 AU passing the star. You're getting power up a maximum of about 30 watts per cubic meter. So the average power over the traverse is about 15 watts per cubic meter. Multiply that out by the size, and you might get a total power coming into reasonable numbers, multiples, maybe 15 watts or so over the distance. This one is just that angle to the magnetic equator, depending whether you're coming in along the pole or whether you're coming in along the equator. Turns out if you come in polar, that 90 degrees, you're going through fewer magnetic field lines, but you're always crossing those magnetic field lines at nearly a perpendicular radius. So it turns out it isn't actually as much of a factor as we had thought. The angle to the magnetic equator is not particularly a major factor. Now, I do need to mention that stars change. They have both magnetic and plasma events. So the solar wind is not a constant at about 9.5 per cubic meter. It goes way up and down. The magnetic field also goes up and down. And this goes even more so for the little red dwarf stars, such as Proxima Centauri. Proxima Centauri has orders of magnitude change in the plasma density as it goes through active and inactive phases. Moving on to the next slide, we can also get some power during cruise from the probe's motion through the ambient interstellar medium, depending on which way we're going, because we have to cross magnetic field lines. But the magnetic field in the interplanetary medium is non-zero, so we can get some power. It depends where we are. Turns out the sun's embedded in the local cloud, somewhere between 0.1 and 0.2 partially ionized hydrogens per cubic centimeter. If we're going to Alpha Centauri, unfortunately, we're going the wrong way. We're leaving the local cloud. We're going to a place where the density is more like 0.001 to 0.05 hydrogen ions per cubic centimeter. So next slide. So the amount of power that we get is going to depend on which way we go. But for a circular sail cross section, multiplying out by that a to the 3/4, if we need 10 milliwatts, just as a arbitrarily picked number, depending whether it's the high or low electron density, it's from 5,000 square meters to 12,000 square meters. That would be sails of 82 to 124 meters, assuming that you're moving across the magnetic field lines. So just sort of a final slide, some of the conclusions. The ultra miniature flyby spacecraft requires a power system that's extremely hard. It's orders of magnitude lighter than anything previously made for a spacecraft, and it's really not a solved problem. There's a number of different approaches. we looked at one. There were some plausible approaches that say it might be possible to do these power systems, but it is by no means a solved problem. And I should point out that this was just the power generation portion we were looking at. Generation is only one portion of a power system. We'd also have to look at power storage if needed, power conditioning, power transmission, etc. So a brief summary of the work we did. I can stop now and answer any questions. Thank you.
So we have one question here. Can this method be used to slow down the sail? And if so, how much deceleration would you be able to get potentially?
Yeah, it turns out not. It turns out that the force that you're generating from these low density particles is way too low to make a noticeable change in your trajectory. As a couple of people had pointed out in years past, if you have a big magnetic field, you might be able to slow down in the ambient plasma. But typically to do that, you're talking essentially cross-section areas of many square kilometers to gather enough of that very tenuous plasma to slow down. The sails on the order of several square meters just is not good enough.
Thank you. And I had several questions, but you answered them in your last couple slides, so I think we're set.
Okay, great.